So with pleasure, I welcome you to this video where I'm going to speak on linear differential equations of the first order. But in this video, I want to focus on homogeneous and non-homogeneous. So I will show you some examples and two particular properties that we need to pay attention to. As you can see on the screen, you will notice that I want to bring to your remembrance the concept of linear. And don't forget that this is very important because in the title I emphasize on linear first order, and we're going to categorize it into homogeneous and non-homogeneous. Now, as you can see now, if you have dy dx is equal to fx comma y, and then we have that particular function fx comma y, and is a function that's depending on y. But in this case, y is in first degree. What does that mean? It means that what we have in there is y raised to power 1. And in that case, we can refer to this one as a linear, because if the function fx comma y, it has a particular y inside of it, and inside that y, everywhere, y is raised to power 1. That is why we mean that y must be in the first degree. Then we refer to this one as a linear. But the only thing we should look at is that there's a summary. And we call this one linear because the dependent variable, which is y in this case, and all its derivatives, like the y dx, just like we have it, it's first order, we only have the y dx, they are in the first degree. What I mean is that the y dx is of raised to power 1. Y is of raised to power 1. And there is no place we are having the y dx multiplying y. That is the key note here. If you can look at what I underlined here, as I said, the dependent variable y and all its derivative, the y ds, they appear only in the first degree. And also, there is no term involving the product of the derivative or any derivative and the dependent variable. So we are going to stick to that formula that with that expression, that what we can see on the screen is actually what's linear. Why? Because we have dependent variable y and it's not multiplying any of the derivative. That's what we mean by it's of the first. Now let's pay attention to the concept of homogeneous and non-homogeneous. Actually, there are many cases that we've solved, but I've not been able to really call your attention to this. That is why I need to bring to your attention that if you have ax multiplied by the y dx is equal to bx multiplied by y plus cx. In this case now, a of x is a function, a of x, b of x, c of x, they are continuous real value functions. What I mean is that a of x, b of x, c of x, they are both functions of x only. And those functions, they are actually continuous and they are indeed real valued functions. So the point now is that a of x is multiplying the derivative of y, b of x is multiplying y. Then the only thing that we have that is left constant is c of x. Then that c of x is what we are going to use to categorize, to classify the problem to either homogeneous or non-homogeneous, because it's the only one that is not having y multiplying 8 now. Now let's take a look at case 1 now. When c of x is 0, we have this expression, and that is what we refer to as homogeneous differential equation. We call it homogeneous differential equation because in this case, our c of x is indeed what? 0. The second case is when c of x is not 0, which will still give us the same problem back, and that is what we refer to as non-homogeneous. Now, if you now look at it now, you cannot see that what we are talking about, homogeneous and non-homogeneous, is when that term that is depending on x alone in the differential equation, if it is there, then we call it non-homogeneous. If it is not there, then we call it homogeneous, and that is only possible if that parameter is 0 and when it is not 0. Now let's pay attention to this now, linear differential equations of the first order, and we are going to focus on non-homogeneous now. Just like I explained earlier that in this case now, our c of x is known as q of x because it's only q of x that is not multiplying the dependent variable y. So that is what we are going to use to classify this as non-homogeneous, because here we have q of x standing alone and is a function of x. And if you look at this one very well, you will notice that it's very familiar. Now that is what we called linear equation. And if you remember in Mode 1 Unit 2C, I've explained to you how to solve this kind of problem, and I said it's very simple. All you need to do is to look for the integrating factor, which is exponential integral p of x dx. And in that case, we have p of x to be the multiplier of y. And when we do that, we get integrated factor, then we multiply both sides of the problem. Then we can now proceed and solve the problem, I believe. If you don't need help, please go and check our video on Module 1, Unit 2C. Example now is this. Let's consider the y dx plus 2y is equal to 2x squared plus 3. This example, you have it in your lecture material, page 83. So they actually use a particular method, variation parameter, to solve it. But in this video, I will solve it using the same method I've used in Module 1 Unit 2C to solve the same problem. So that's what we're going to consider now. So what is the integrating factor? Integrating factor is exponential integral 2 dx, because p of x in this problem is what is 2. So then we multiply both sides of the problem by exponential 2 dx, and then we give us exponential 2x multiplied by the y dx. Then we have 2y again multiply exponential 2x, and we have 2x squared multiplying exponential 2x, and we have 3 multiplying exponential 2. So the next thing we're going to do now is that, as you can see clearly now, we're having the problem as it's a way now. But if you look at it, there's something you need to note, that this one is more or less as if, I'm talking about the left-hand side. It's more or less as if we have d dx of y multiplying the integrating factor. Because if you keep y and you differentiate exponential 2x, you have 2 exponential 2x multiplied by y. And if you keep exponential 2x, you differentiate y, you have e2x multiplying the y dx, which means that you're still having the same problem. So now let's try to make ds to go to the other side, where we have d multiplying y exponential 2x. So the next thing now is that we integrate both sides. And when we integrate both sides, you now see that this one will give us integral, we take care of d, then we have the other side. So the next thing now is that we have y multiplying exponential 2x. Then if you look at this one, we can separate the integral to take care of 2x squared exponential 2x dx, plus then you take care of s integral, then 3 exponential 2x dx. So in that case, you notice that we may need to use. So if that is the case, then we need to integrate twice. So in our WhatsApp group, you notice that I sent a particular picture to us where I solve this integration using by part twice. So if you do it, what you have is the one you can see in red fonts. So which means that we can now obtain by the time we substitute the integration by parts into the expression, we now have it to be y multiplied by exponential 2x, then 2 we multiply the whole thing that we come up with, then plus 3 over 2 exponential 2x, then constant of integration plus c. So we now obtain, in this case, the exponential 2x can go to the other side, can divide both sides. So when we divide both sides by exponential 2x, then what we obtain is this. As I can see now that we now have y standing alone. So with that, we can now see clearly now that 2 can divide both sides, so the other side. So we have this expression to be the solution. So you can now see now that we've been able to solve this problem, which we refer to as linear first order ordinary differential equation. So that is case 1. Now there are 2 properties now that I need to explain to you. The first one is called superposition principle. What this one is saying is that let's assume that we have a particular problem. Most times this is not always realistic in the case of first order, but there are some cases in first order which we are going to see in this problem, like in the case of homogeneous, non-homogeneous. In the case of non-homogeneous, which is actually non-linear, but first order, it's possible for us to have 2 solutions that satisfy. In fact, we're going to solve in the next video. I will introduce you to what is called riccati. In the case of riccati is actually first order, but it's like an advanced problem of Bernoulli. In that case, we can have 2 solutions which are correct. So based on that, we can come up with what is called superposition principle. What it's trying to say is that if you have 2 solutions, y1 and y2, we are very sure that y1 and y2, if we put them into the problem, it will give us the other side, which means that the two solutions can satisfy the differential equation. So number one is that if you multiply that particular one of the solution by c, cy1 is also a solution. In fact, if you add the two solutions together, you will still satisfy the problem. That is what we call superposition principles. In fact, C1 multiplied by the first solution plus C2 multiplying the second solution is also another solution. So this is what refers to as a superposition principle, which just helps us to know that if we have two solutions to a particular problem, then there are three things involved, which, as you can see on the screen. Another important thing now is the case of complex valued function, which is a solution. What we're trying to say here is that if we have a solution and that solution is term of complex, I know when we have complex, it has to do with real plus the imaginary. Okay, so in this case now, if y is equals to p plus iq is indeed a solution. Now the p aspect of it, are we together, which is the real part, is also a solution. The q aspect of it, which is the imaginary, is also a solution. The next thing we're going to study now is called zero solution. And this case of zero solution, if you have y is a solution of the equation on high, we call it a zero solution in the sense that if you have a solution y and then there's a point on the interval, on the independent variable x, in such a way that if you put that point into the solution, you have zero, then it means that y, which is the solution, is also zero on that I. We refer to this as zero solution. So you can now see now that there are three major important properties now, which are actually available for even either homogeneous or non-homogeneous. So we just call them some properties of the solution. So the three now is a superposition principle, complex value function as a solution, and zero solution. So that those are the. Now let's take a look at this Bernoulli equation now. You will see that we call this one Bernoulli because q of x is multiplying y raised to power n. And the most important thing about this is that this problem here can reduce to linear if n is 0, because anything over 0 is what is 1. But in this case that we have y raised to power n, we refer to this one as Bernoulli. And this Bernoulli, we can reduce it to linear equations. If you need any help, please go and check our past video. That is Module 1 Unit 2D and Module 1 Unit 2D2. There I was able to solve some problems on Bernoulli. But what we can see here is that we can actually reduce it. But in this case, remember that this is what we have on the board is actually non-linear, because n is greater than 1. Are we together? And in fact, if you look at this, by the time we have y, even if we have y to be raised to power 1, are we together? You see, because we can still call it Bernoulli. But most times, by the time we have n equals to 2, in that case we have y squared, and that makes the problem to be non-linear. So we can actually refer to Bernoulli equation as non-linear, because in this case, y is the dependent variable. And by the time we have this to be y squared, then we can call it non-linear. And at the same time, this problem here, it can be reduced to non-linear, and at the same time is indeed non-homogeneous. So please take note of that.